You're sitting in the window seat. The plane hits some rough air. You glance outside and the wing is moving. Not a little. It's bending, visibly flexing up and down like it's made of rubber, and your stomach drops. You grip the armrest. You're convinced something is wrong. But here's the embarrassing part. You just watched the single most important safety feature on that aircraft doing its job perfectly. So, why do wings bend? What happens if they didn't? How much can a wing actually flex before it breaks? And why does every nervous flyer have this completely, totally backwards? A wing isn't a rigid plank bolted to a metal tube. It's a long, carefully shaped beam designed to carry enormous loads while passing through air that never stops moving, shifting, pushing, and pulling from every direction. Think of a diving board. A stiff wooden board cracks under repeated impact. A springy fiberglass board takes hit after hit and bounces back. What the wing is the springy board. The bend isn't a flaw. It's the whole design. But here's what almost nobody knows. Most people assume rigid equals safe. That makes total sense on the ground. You don't want your chair flexing. You don't want your floor bouncing. So when you see a wing moving, your brain screams danger. The problem is that instinct is built for the ground, not the sky. And when engineers in the early days of aviation tried to build wings that felt rock solid, the results were catastrophic. Rigid wings were tried. They failed. But the reason why they failed is the part that surprises people. Air isn't smooth. It's messy. It has pockets of fast-moving air, pockets of slow air, sudden gusts, and pressure changes that happen in fractions of a second. Every moment of flight, the wing is getting hit by forces coming from different directions at different speeds. Now here's where it gets crazy. When a rigid wing takes one of those hits, it doesn't soak up the force. It passes the entire load directly into the body of the plane, the bolts, the joints, the frame. Every single hit goes straight through, and metal under repeated stress does something slow and invisible. It fatigues. Tiny cracks form. They grow, and eventually the structure fails without warning. A flexible wing works completely differently. When a gust slams into it, the wing bends. That bend spreads the force along the entire length of the wing. Unlike how a long whip absorbs energy along its length instead of snapping at the handle. The force gets soaked up gradually, then the wing springs back. Engineers call this load alleviation. The wing flexing is literally protecting the rest of the plane from the full impact. The bend you're watching in a panic is the wing taking the hit so the rest of the aircraft doesn't have to. That's not the plane struggling. That's the plane winning. Now, this is the part everyone misses. Engineers don't just allow the flex. They calculate exactly how much flex is safe, test beyond that, and then test even further. The Boeing 787 Dreamliner, for example, has wings that were tested to flex upward by 26 feet during ground tests. 26 feet. That's taller than a two-story house, measured just from the wingtip moving upward. And that's not the breaking point. That's the point where engineers stopped the test because real flight will never come close. During the worst turbulence you'll ever experience, those wings flex about 3 feet. 3 feet versus 26 feet of tested flex. The wing you're watching bend during a bumpy flight has already survived a simulated flex more than 8 times that size on the ground before the plane ever flew. You're probably thinking that modern wings are just smarter. But actually, nature figured this out roughly 150 million years ago. Bird wings flex constantly during flight. Every beat, every gust, every turn. The bones and feathers distribute force and spring back. Early aviation engineers who studied birds closely moved toward flexible designs faster than those who studied rigid structures like bridges and steel beams. We basically reverse-engineered birds, but used aluminum and carbon fiber instead of hollow bone. Nature solved the problem. We just took a while to copy it. And then this happened. And it changed everything. It's 1952. The de Havilland Comet has just become the world's first commercial jet airliner. It's fast, sleek, and prestigious. Engineers are proud of it. Passengers love it. But the Comet had square windows. Sounds like a small detail. It wasn't. The corners of square windows create intense stress points, places where force concentrates instead of spreading out. Combined with a fuselage designed around rigid stress assumptions, the metal around those corners began to crack invisibly with every pressurization cycle. Every takeoff, every landing, every flight added another tiny crack. Within 2 years, 3 comets broke apart in midair. Investigators worked almost like detectives, reconstructing the wreckage piece by piece, and discovered that the design had been treating flexibility and stress distribution as problems to remove, when they were actually the solution. The crashes forced the entire aviation industry to rebuild its thinking from the ground up. Every oval window you've looked through on every flight you've ever taken exists because of what those investigators learned from those three disasters. The smooth, rounded shape spreads stress evenly around the frame instead of concentrating it at corners. The oval window above your seat isn't just aesthetic. It's a direct result of learning that rigid thinking breaks things. So, when you start noticing this logic everywhere, you can't unsee it. The Taipei 101 skyscraper in Taiwan has a 660-ton steel ball hanging inside it, a giant pendulum that swings in the opposite direction of an earthquake to let the building sway safely instead of crack. The Golden Gate Bridge flexes up to 16 feet vertically in high winds, by design. Your phone's Gorilla Glass survives drops because it's built to flex microscopically before cracking. A fully rigid screen would shatter instantly. Running shoes have flexible soles because a rigid sole sends every foot strike directly up into your bones, causing stress fractures over time. Ski poles are designed to bend on impact so the force doesn't transfer straight into your wrist. Carbon fiber road bikes flex slightly side to side to absorb road vibration over long rides. On trees that grow in constant wind develop flexible trunks. Trees in sheltered spots that never sway become brittle and snap in the first real storm. Guitar strings work because of tension combined with flex. A perfectly rigid string couldn't vibrate and would make no sound at all. Human bones are slightly flexible. Fully rigid bone would shatter on the first hard impact. Massive container ships flex visibly along their length when crossing heavy ocean swells. Engineers design that flex in deliberately so the hull doesn't crack. Even spacecraft solar panels are deployed with controlled flex to handle the extreme temperature swings between sunlight and shadow in orbit, where temperatures can swing by 300 degrees in minutes. But where strong almost never means rigid. It almost always means controlled flex with known limits. But here's the real trade-off nobody talks about. Flex has a safe zone. Engineers calculate something called the elastic range, the zone where the material bends and returns to its original shape. Stay within that zone and the wing is fine. Push past it and you get permanent bending or fracture. The real danger for aircraft isn't turbulence bending wings. It's the slow buildup of fatigue from thousands of small flex cycles over years of flying. Every pressurization cycle, every landing, every pocket of rough air adds a tiny amount of stress to the material. This is why planes aren't just retired when they look old. They're tracked by flight cycles, the number of times the airframe has been pressurized and depressurized, the number of landings, the total hours of stress exposure. A plane isn't certified just for flying. It's certified for a specific number of flex events. Once the count gets high enough, the plane gets pulled from service regardless of how it looks. Modern materials like carbon fiber composites, a material made by combining carbon threads in a resin, handle fatigue cycles far better than aluminum, which is one reason the 787 uses them so heavily. The flex is managed. The limits are known. The system works because nothing is left to guesswork. Wings bend because bending is the answer, not the problem. The wing that stays perfectly rigid is the one that eventually cracks. Next time you're in the window seat and the wing flexes, don't grip the armrest. Nod. You're watching engineering work,